Okay, for this lesson, we're going to take a look at maximum and minimum values. One of the most useful things we can learn from a function's derivative is whether the function assumes any maximum or minimum values on a given interval and where these values are located if it does occur. Once we know how to find a function's extreme values, we'll be able to answer such questions as, what is the shape of a can that can minimize manufacturing costs? So when we're investigating these max and min values, we're given the graph of a function that's shown on the right here. When it says, what point is the absolute highest point that occurs on the graph? We can very clearly see that there's my highest point at 9 and 7. This point is called the absolute maximum of this function. We say the function has an absolute maximum at 9, where x is equal to 9, and the maximum value is f of 9 is going to be 7. So even though the maximum is occurring at an x value of 9, the value of that maximum is the y value. What point is the absolute lowest point on the graph? Well, that exists right here at the point of 2 and 1. And we're going to call that our absolute minimum. We say that the function has an absolute minimum at 2, and the value of the minimum is f of 2 is equal to 1. The y-coordinates of a maximum and minimum points are said to be the extreme values of the function. So in the case above, the extreme values are 1 for the minimum and 7 for the maximum value. Notice that if we only consider the section of the function in between 2 and 6, then we can find a local maximum or relative maximum at this point. And that is at 4 with a value of 5. When it says, is there a local minimum on the graph and in what interval does it occur? Well, there's another minimum point that we can see here. At the point of 6 and 2. Where does this occur? It occurs in between these two maximums, so it occurs in between 4 and 9, or on the interval of 4 and 9. When does this occur? It occurs when x is equal to 6. And what is the value of it? The value of the minimum is 2. Well, this looks like another minimum point, but when it says, is this point also a local minimum? The answer is no. And the reason for that is local minimum cannot occur on an endpoint. So it can only be where the graph is continuous. It can't actually be on an endpoint for a local min or local max. Can a local maximum also be an absolute maximum? Well, this minimum wouldn't work because that's on an endpoint, but we can see that the maximum here is still when it's continuous, which means that that could also be a local max. And this is a local maximum in between 6 and 12. When it says, do all functions have a maximum and or a minimum value, considering y is equal to x squared and y is equal to x cubed? Well, if I graph the first one out for y is equal to x squared, then what do we see? We see that this one has a minimum, but it has no maximum. When we do y is equal to x cubed, then in this case, there is no minimum or maximum. So we can have multiple minimums and maximums occur, whether they're local or just a singular absolute one, or we can have none of them occur. If we're doing the definitions, let f be a function with the domain of D, then f of c is the absolute maximum value at c on D if and only if f of c is greater than or equal to f of x for all x in the value of D. An absolute minimum at c if f of c is less than f of x for all x in D. A local or relative maximum or minimum if f of c is greater than or equal to f of x when x is near c. When we're connecting this to the derivatives, recall that the derivative of a function gives us the slope of the tangent line at any point, xy, on the function. We also know that, however, that not every point on the function can have a derivative. So for these examples, there's no derivative at a, since there can be no tangent line that occurs at a. So we could have one case where if I have the point A and I have a vertical asymptote occurring at A, or I have the point at A and I have a jump discontinuity that is happening at A. We can say that if f is discontinuous at A, so f of A does not exist, then f prime of A does not exist, because remember that the derivative always has to have a domain that is a subset of the original function. In the next two examples, even though my original function is continuous, there is no derivative at a since no tangent line can be drawn at a. So this is when f of x does exist, but f prime of x does not exist, in this case, for a. So we could say that if we have a here, and we have a cusp, or a corner that's occurring at a, or if we have a here, and the original function becomes vertical at a, then for both these cases, f prime of a is not going to exist. When we talk about critical numbers are the x-coordinates of points on a function where the slopes of the tangents to the curve change direction. At these points, the slopes of the tangent line are either 0 or undefined, as the slopes change from being positive to negative or negative to positive. And when we think of it that way, that happens when f prime of x is equal to 0 or f prime of x is not defined. It's important to note, vertical asymptotes are not critical numbers since they don't exist in my original function. So a critical number has to occur in my original function, even though it can not exist as my derivative.